Well, hello everybody. Thank you very much for coming. I'm Clemens. I'm here to talk about the topic that's very near and dear to my heart, which is computation in Bitcoin. It's a topic I've been working on for a pretty long time, over 3 years at this point. And so what fascinates me about this topic is that I think Bitcoin can be used for many things that's not being used for today, right? And in particular, I mean, actual full applications can be built directly on Bitcoin, just like they're built on Ethereum today. And so I think that's actually kind of great news for everybody who's in Bitcoin, everybody who owns Bitcoin, because I'm thinking this makes Bitcoin a bit more useful. And so very excited about this topic. And previously I gave 2 talks. I gave one talk about a year ago in Tokyo called Why Bitcoin is Turing Complete. And what I showed there is basically that the data structures of Bitcoin are sufficiently powerful to simulate the run of a Turing machine, right? And that's sort of the first prerequisite we'd need if we ever wanted to do full computation on Bitcoin. And then a couple of months later, I gave a second talk in San Francisco called a Smart Contract Engine for Bitcoin, where I sort of made this approach a little bit more concretely. And in that talk, I explained how we can sort of reuse old ideas in Bitcoin in the field of colored coins and just like upgrade these ideas slightly and exploit the techniques there a little bit more to actually build a very powerful smart contracting engine on top of Bitcoin. But that project, while I think many very interesting applications can be built that way, it's a system that's not super easy to use. So it's much more comparable to programming in assembly code, right? And of course today everybody loves to program in these higher level languages like JavaScript and Java and stuff like that. And so that's what I've been working on for the past couple of months. And so now I'm very happy to be able to present this to you. I'm calling this thing the Bitcoin computer. And what it allows you to do is to write smart contracts in JavaScript and run them on Bitcoin. So let's jump right in. Overview about what's going to come. I'm going to talk for a little tiny bit about smart contracts and just explain what they are and where they come from. And then the biggest part of the talk is going to be about the Bitcoin computer, the software that I'm building. So I'm going to explain what that is, what it does, and how to use it. And finally I'm going to wrap up. So let's jump right in. So it's the shortest possible history of smart contracts. So we all know that Bitcoin got invented in 2009, and that was, in my opinion, really one of the major breakthroughs in computer science in the past decades, really, right? Because what it allows you to do is run one very important application, which are payments, run them in a way that doesn't sort of require one central point that everybody needs to trust, right? And that was something that had been tried in academia, but they couldn't really pull it off. And so Bitcoin was the first system that was actually practical, that scales to a large number of users, and that allows them to send payments between one another, without requiring trust in a third party. And then, in my opinion, surprisingly early on, as early as 2012, when the Bitcoin community was very, very small, in fact, some amazing work was done, in my opinion, in the area of colored coins, and there were several teams competing on the ideas like that. And sort of the general approach or general thinking was, okay, we have Bitcoin, and Bitcoin has showed us how we can build payments in this decentralized setting. Can we use similar ideas to build more applications than just payments, right? And then sort of colored coins were the first example where sort of Bitcoin was taken to not just to send money around, but to build other things, right? And these other things were mostly tokens that can represent real world assets, and you can send them to your friends, or you can collect them, or you can trade them if you want to. And so this is sort of the second layer here in my little chart in terms of what you can do with crypto, right? So those areas we can do just payments. Middle layer means we can, in addition to payments, also do tokens pretty much. And another 2 years goes by, and eventually Vitalik Buterin, who actually came out of the Colored Coins project, so he contributed to this project and had great ideas there. 2 years later, Vitalik released his own cryptocurrency called Ethereum. And Ethereum, in terms of the application that it could build, went not just one layer up, but really sort of to the maximum layer, right? So every single application that can be built on any computer can now be built on Ethereum in a decentralized way, which has many advantages, as people know. So pretty much since then, I don't think there's been a major breakthrough in terms of making smart contracts work better for cryptocurrencies. So there's been a bunch, mostly during the ICO craze of, the last 2 years. Many other coins were launched, and, many of them also have, Turing complete smart contract capabilities. But mostly what they did is they just, I'm going to say they're strongly inspired by Ethereum, and sort of, a bit less of a breakthrough ideas. So what didn't change at all is sort of the state of Bitcoin, the applications you could build in Bitcoin, right? And so Bitcoin and Ethereum are quite different technically. So you can't easily transfer the ideas from Ethereum onto Bitcoin. That just doesn't work, right? But now I've been sort of, banging my head against this problem, like I said, for a long time. I spent a lot of time in university studying problems like this. And so I think over the last few years, I got, a few pretty good ideas for how we can actually build smart contracts directly in Bitcoin. And, that's what I'm here to present today, pretty much. So what's the Bitcoin computer? Long story short. So, before I go ahead and explain what I mean by the Bitcoin computer, let's just look at, what's even a computer, right? And sort of on the most abstract level, computer has two components, has a CPU and a memory, right? So, if you look at, a book about hardware, there's many other things in a computer, but they're really, the purpose of all the other things is just to keep these two things alive and working pretty much. So what are they good for? Memory is, just a storage device for data, right? Where you can store your data here. And when I say memory, there's a big hierarchy in memory, starting from, processor caches to, hard drives. I just mean anything that stores data here. Sort of the second component is, the CPU. That's where sort of the actual computation happens, and or a different way of putting it is where sort of the data gets updated. Okay, and that's a very basic. These are the two basic components that any computational system have, right? So I'm starting from Turing machines, and all examples there's always sort of storage and a way to update that thing. Okay, and if you don't want to be completely abstract, you also have to put a human in the loop there somewhere. Why have a computer if the humans can't learn anything from them? And so that's why to other important components of a computer is, of course, the input and output devices. And so in general, computation can be explained that as, a user gives an input to a computer, and then there's something crazy, magical happening in here, all this computation stuff. And the result of all this crazy, magical stuff is that, number one, the user gets an output. So the user can ask a question, and the computer can give the user an answer. And also, the computation can have what's called side effects, where sort of the memory changes its state. Okay, so that's very basic computer. And then it's actually kind of interesting if we compare this to Bitcoin. In Bitcoin, we also kind of have these two basic components. Okay, so on the one hand, we have the blockchain, which is a data storage device, and pretty good one actually. I'll talk about that. And you have the miners, whose job it is to update the blockchain. Okay. So in a sense, if you want to, you can view this as, here's your memory component and here's your CPU component of the, Bitcoin computer. But unfortunately, Bitcoin as a computer is quite restricted. Okay, so I don't know if you can tell this from the slides, these processors here, they're really, really small. Okay, they actually can't compute that much. And even more dramatically, this output arrow is really, I made it thin here because kind of the answers you get back from Bitcoin are not as good as the answers you would get from a normal computer. So in particular, really what you can only do with Bitcoin is you can send transactions to it, and your computation component, the miners, will verify, is that a valid transaction? If it's a valid transaction, it gets added to the blockchain. If it's not one, it will just tell you no, right? So there's only limited amount of information that you can get out of Bitcoin. And in a sense, Bitcoin is a little bit closer maybe to a storage device than to a full computer. But then, like I said, Ethereum got invented. And on a very basic level, you can think of Ethereum, it has a blockchain, has a kind of a similar data structure, similar properties to the one in Bitcoin. On a technical level, it's a little bit different, but taking a step back, it's very similar. But now we gave the miners much more power here. Okay, so I drew them a bit bigger. And so these are now sort of full-fledged CPUs that can perform arbitrary computation. Okay, and so now this, in terms of functionality, works exactly like a normal computer, right? Where a user can send an input to the device, and the device performs a computation, updates the state on the blockchain, and returns a result. Okay, so my mission is here to, I've set myself up to building, turning Bitcoin into something where you can do computation. So the mission is to build something like Ethereum from, Bitcoin here. But like I said, the problem is that sort of on the computation side, Bitcoin's a bit weakish, and there's nothing I can do about that really. So I'm going to need, some help. I need another tool, and the only tool that I can think of really is just a good old computer. Okay, so now that we have all these things on the screen here, let's just compare what's going on. Okay, so computers have been around for a long time, and very popular devices, can do amazing things. And if you compare, say, Ethereum to the computer, what you see is that the computation, the CPU component of Ethereum is actually kind of like less efficient than the one on your good old laptop, right? So number one, all computation in Ethereum is replicated 10,000 times. Okay, if you send a command to the Ethereum network, there's about 10,000 miners, and all 10,000 miners will execute your program for you. Okay, and they will all compute the same result because it's the same program on the same inputs, and then they will update the blockchain accordingly. Okay, so just by having the computation run on 10,000 computers instead of just one means increases your costs by a factor of 10,000. But unfortunately, it's even worse than that, where these miners have to talk to one another, right? And they have this sort of very complicated and inefficient pretty much communication protocol between them, which they need to have because of the Byzantine environment that they work in. But still, sort of that adds another factor of 100 or 1,000 in inefficiency. So overall, these computers are like 1,000,000 times more costly to use than just the processor on your hard drive. Okay, so I mean that sounds disappointing. So why is everybody so excited about crypto? And the reason they're so excited is because this storage component of crypto is really very, very novel, and has very many good properties that just the normal hard disk doesn't have. Okay, and so the examples are, if you update your normal hard disk, your previous state is pretty much just lost forever, right? Or very, very hard to recover, if you can recover it at all. The blockchain just stores every previous state, right? So whenever you want to go back in time and see what happens, you just sort of check into this log, that's the blockchain, figure out the previous state, right? Other things is that every single update on a blockchain is cryptographically signed. So you know exactly who performed which update, and it's also time-stamped. Okay, these are all features that are not here. And finally, the biggest advantage is that these blockchains work really, really well in a multi-user environment, right? And so that's why they were originally invented. You wanted multiple people to come together and sort of create, a shared history of computation of what happened. And so blockchains work very well in multi-user environments, but even more impressively, they work in multi-user environments where everybody hates everybody else and everybody tries to cheat. And so these are very, very good devices for storing data, and in particular in a Byzantine environment. Okay, so coming back to my task here, we got a good old computers. They're amazing at computing stuff, less impressive at storing stuff. And we got the blockchains that very, very good at storing things. Ethereum and Bitcoin pretty much alike. Ethereum also has these very expensive, but at least they can do computation. Bitcoin doesn't even have computation. Okay, and so once you have it on a slide like this, it doesn't really seem that hard. So let's remove this guy here. So the basic idea is if Bitcoin shines in storing data, and the laptop on your desk, the device you're looking at right now, excels at computing stuff, and every computer has these two components, why not just combine these two? Okay, and that's the Bitcoin computer. Okay, it uses a normal computer, the computer on your desktop, to do computation, and then it uses the Bitcoin blockchain to store things. Okay, and you have to have them talk to one another. So you remember in the in the old picture of computers, I showed you there's the system bus, which handles all the communication between the CPU and the memory. And so in the case of the Bitcoin computer, we just make sure that we always keep the data on the computer in sync with the data on the Bitcoin network. Okay, and this is how we bind together the blockchain with your computer on the screen. Okay, and so why would we do this? Okay, so this, it's a very good storage device, but it's also pretty expensive to use. You have to pay for every time you access the database. But the main reason for doing this is that the properties, you can unlock the properties, the special properties that only blockchain have, and make them available in a normal computing environment by coupling these components so closely. So let me show you one example. So this is an example of a single user system. I just told you that Bitcoin works great in a multi-user environment. So what happens if we have two users now, and they both have their own computers? This is the computer owned by this guy, and this is the computer by this guy. What happens if they both synchronize their computers to the blockchain in that way? Okay, so what happens is this guy can provide an input, change the state on his local computer, because his state is completely synced to the state on the blockchain. This change will propagate to the blockchain. And now, since the second guy here is also synchronized to the blockchain, his device will also update, right? And so if you abstract away all the details in the middle there, to these two guys, you don't have to be bothered with how it works inside. To these two guys, it really feels like they're just using one computer, right? And so in particular, these are not just, you can't just do this for two people, you can do this for groups of people, and eventually for everybody on the planet, right? And sort of the promise of Bitcoin computer is that we can use the system, and it works as if we were sitting all typing into the same laptop, which has great advantages in many, many applications. We'll mention some of them later. But that's what the Bitcoin computer is. It's the one global computer that's been running for 10 years, and we can all use it together. And we can use it for all sorts of business purposes, games, many different things. But actually, there's more advantages to this construction, okay? So I mentioned before that, these blockchains have properties that normal computers actually don't have, right? And then, one of the most well-known properties is money. Okay, you can use Bitcoin was created to send money around, so money is just baked into the system. And by creating the Bitcoin computer, we just sort of make money available in your normal computing environment, right? So you can now think of this as a computer that doesn't just store data and process data or update data. In addition, it can also store money, okay? And that's a property that doesn't exist in computers today. And that's what makes the Bitcoin computer a very special computer, a very unique computer. Of course, you can have money in current computing environments. You can use a service like PayPal, but money is just not baked into computation from the start. And sort of by coupling the blockchain with normal computers and creating the Bitcoin computer, we make money available, easily available for use in computing environments. And there's actually more features of the blockchain, right? So as soon as you have money, you have to protect money somehow, right? So it's a storage device for money where everybody can see that doesn't make sense. So we're designing, of course, the Bitcoin computer to store the money just as securely as your money is stored on the blockchain, right? And the reason it's stored as securely is just because it's the exact same way you store money in Bitcoin right now is exactly the same way that the Bitcoin computer stores money. But then the way that Bitcoin protects the money is that it ensures that only the owner of that money can send that money somewhere else, right? Which is a very sensible thing to do. And so we have this notion of an owner of a coin. And so we can very easily just make this notion of ownership also available in the Bitcoin computer. So which is the second additional property that we're sort of adding to normal computation, which is this notion of ownership, right? And an owner can mean you have a user assigned and only that user can send that money somewhere else. But we're also extending ownership not just to money, but also to data. Okay, so in the Bitcoin computer, we have a very strong notion of data ownership. So if you own a piece of data, you're the only one who can delete that piece of data. You're the only one who can update that piece of data. You're the only one who can modify that data. You have complete control over that data. Nobody can take that away from you. Okay, and so that's sort of the second component that the Bitcoin computer adds to normal computing environments. Okay, and that's pretty much it. So this is, to me, an abstract explanation for what the Bitcoin computer does. It has a component where it does everything that normal computers do, whereas it has memory and a CPU, but it also has two additional features, which are money and ownership. Okay, and then, okay, there's even more features. So of course, every update is time-stamped and digitally designed, but that's not the focus of our talk. But then these are very useful features that will come in handy later. Okay, so now let's make things a bit more concrete. How are we going to use the Bitcoin computer? And then, as usual, I like to just take inspiration from what exists. So let's focus on normal computers at first. So we need, every computer needs some sort of development environment to make it sort of easily accessible. So really, computers are usually accessed through applications, and we need some sort of techniques to build applications. The way to build applications in normal computers is you write a program in a programming language, and we have many great programming languages. I just put a couple of examples here. And in addition to your programming language, you need some sort of deployment infrastructure that makes sure that your program is running on your computer, and then keeps running, and all these kind of things. So what can we learn from this now that we want to build sort of a programming language and a deployment infrastructure for this slightly more complicated device here? Okay, so first of all, the first thing we learn is that the Bitcoin computer is not an entirely new computer, no entirely new invention. It's partially something that's old and existing and very well understood, which is computation on data, and two additional things. Okay, and so in my opinion, there's no need for us at all to reinvent the wheel here, create a new programming language. We should, just pick one of these programming languages that people have put, decades of work in to make them, really, user-friendly and sort of nice things to use. And, we're just picking the most popular programming language that there is today. So the programming language that's used to program the Bitcoin computer is mostly just JavaScript. Okay, and so we're picking JavaScript for two reasons. Reason number one is, according to certain studies lately, it's the most popular programming language ever. Right? So apparently around over 70% of programmers already today know how to use JavaScript. And so if we're sort of launching a new smart contract platform, it seems very helpful to use a language that everybody already sort of likes to use. And the advantage is there that companies don't need to hire new expensive smart contract developers, and then they'll have to train them and explain to them which smart contract to write. Instead, they can sort of have their existing employees who are already domain experts write the smart contracts, right? And so that seems much more secure approach. And the second reason is there's a bunch of people who are very, very experienced in working with JavaScript for many, many years, and so the probability of making a mistake in your code or introducing a bug or a security problem, it's much lower if people program in languages that they've used for years, right? So these are all reasons we're using JavaScript. And then there's another reason where JavaScript is it's not the most efficient language, and it's probably not the prettiest language, but there's one thing that distinguishes JavaScript is that it's the only programming language that runs directly in the web browser, right? And to me, that's a difference not in quantity and not in how fast it is. It's a difference in quality, right? It's something where JavaScript can do something completely different. And so that's the reason why I think JavaScript can get away with being a little bit, more maybe inefficient or awkward to use than other languages, because it has this one superpower, right? And that's running in the web browser. And we, by all means, want the Bitcoin computer to connect as seamlessly as possible to the internet. So that's why we're using JavaScript. Okay? Now that we have JavaScript, that should sort of cover what we need to do on just in terms of traditional computation. So now we just gotta take care of these two things that we've added to our computing environment: money and ownership. How to deal with them? Okay, so what's money? It's what do you want to do with money in a computing environment? So really, at the first point you want to store it somewhere, right? And then if you look at JavaScript, JavaScript's an object-oriented programming language. So that means it's sort of the basic entity that people use are objects, which are sort of collections of data, and then every object has coupled with it, a couple of functions that tell you how to update that data. Yeah, which is, by the way, very close to the distinction between, state and updates again. Okay, but so we have money, we got to store it somewhere. The only thing to store stuff in object-oriented programming languages are in the properties of an object. So, how about we just say every object in our smart contracting language can store an amount of money. Okay, so it's just, to me, a very, very simple explanation for how that works. And syntactically, what we do is we just sort of add one extra property, which pretty much acts like a keyword inside the Bitcoin computer. It's called amount, and you can set it to a number. And sort of the meaning of that keyword is, if you set the amount of an object to a certain number, and you deploy that object to the blockchain, that object will store that amount of Bitcoin. Okay, and of course you can only do that if you own that amount of money. But if you do have enough Bitcoin, you can just create an object on the blockchain, store money in it. Very easy. Okay, now what's ownership? What does ownership mean? Ownership is like, an owner is a person who owns something. Okay, we just talked about things to own in object-oriented language is probably like an object. Okay, and so what we just do is we just add a second property to every object. It's called _owner. And you can set it to a public key or a list of public keys that specify who is the owner of that object. Okay, and so like I said before, the owner of the object, the meaning is if you own a piece of data, it's like your private property. Nobody can change your private property. Okay, if you own a piece of data, you're the only person who's allowed to change that thing, and nobody can take that away from you. Okay, and in a programming environment, you just set this property of an object to a certain public key, deployed to the Bitcoin computer. And that will ensure that only the owner has permission to update that object. Okay, so and that's all that we need in terms of programming language. So if you're a developer, there's a 73% chance that you know now how to program the Bitcoin computer, right? Because all you need to know is just JavaScript, and you gotta wrap your head around two little properties, one set to a number and one set to a public key. So what do we need in terms of deployment infrastructure, right? Turns out also not that much. What do you want to do with these objects? You want to you want to somehow store them on the blockchain, right? You want to somehow get them into the Bitcoin computer in the first place. So that's where sort of the keyword computer.new comes in. It's very similar to the JavaScript keyword new. The JavaScript keyword new creates a new instance of a class on your local hard drive. Computer.new creates a new instance of a class on the Bitcoin computer. Okay. Very easy to use. Computer is just the NPM package that we expose. So you can download the computer class from NPM and create a new instance, and then your instance will expose the new function. And the second function has to do with the fact that we're trying to make it easy to build these multi-user experiences. So they kind of work together, and the idea is computer.new will create a new instance that's stored on the Bitcoin computer. And then if a second person is also interested in the same object, wants to call a function, for example, they call computer.sync on that object, which sort of creates them a local instance of that same file. Okay, so this is sort of creating a new object on the Bitcoin computer, and this is to connect with an existing object. Okay, and then in terms of if you're interested in learning how to use the Bitcoin computer, this is what you need to learn. Okay, there's no new language involved there. Yeah, I mean, you probably know JavaScript. You got to wrap your head around these two properties. Amount stores a number, which specifies an amount of Bitcoin. Owner stores a pub key, which designates a user of an object. And you got something to deploy a smart contract and something to connect to an existing smart contract. So it's really, I think, very easy to learn. Okay, so the design process was guided by two principles. If you want, you can call them the golden rules of Bitcoin computer, and I've mentioned them already. The first one is very important. If you own a piece of data on the Bitcoin computer, you're the only person who can ever update that data. Okay, and that is guaranteed. Beyond very large amount of force. Whoever wants to try to take your data away from you, it's going to be very hard if you store it on the Bitcoin computer, right? And the reason is that we store data on the Bitcoin computer just using the same techniques and just as securely as the Bitcoin blockchain stores money. Okay, And so that's you know, maybe, you know, it's an important goal, but it's also something that is so fundamental to us that it's not even really part of the thing that we're building. So this is just guaranteed by the Bitcoin miners, right? So that's a very, very important property, and that will always be true. And, you know, the second property just pretty much says that, you know, what we're building here is a good multi-user environment, okay? So we talked about the fact that, like, you know, multiple users can somehow connect to the same object that's stored on the blockchain. And, you know, the second golden rule says that all users must have consensus over the current value, right? And that just means if, you know, Joe from Japan looks at an object and you know, who knows, Sue from Chile looks at the object, at every point in time, they're seeing the exactly same value there, okay? And that's pretty much exactly what creates the illusion of two people who sit on opposite ends of the planet, that they're actually using the same computer, okay? So let's make this a bit more concrete and look at some examples. So here's the first example of a smart contract. It's a counter class, and it implements a counter. A counter is a device that can store a number, and you can increase that number. So the way you implement that in JavaScript is you declare your class counter. It stores one property I, which is, you know, of type number, so it's technically, you know, flow or TypeScript or whatever. You have a constructor to create a new object. That constructor initializes the variable I, property I, to 0. You got your increase function that increases the value that's stored, okay? So here's your first smart contract on the Bitcoin computer. And as you can see, it's completely vanilla JavaScript class, okay? And so this is just sort of the side effect of what we said before. Like, the Bitcoin computer is not some completely new, you know, computing environment. It's just like something existing, storage and you know, CPU, with two added things. So every program that should work on, you know, the simplified version of a computer, which is a normal computer, should also just run on the Bitcoin computer, right? And so in particular, it's going to be one of our goals that every single JavaScript program can run without modification on the Bitcoin computer, okay? And the advantage there being is that existing code that has already been developed, has been in production for years, has been tested and, you know, shown to be bug-free, you know, we want that kind of code to be able to be easily deployed on the Bitcoin computer, right? Because this is highly trusted code, and again, it just, you know, decreases development costs by a very large factor, and mostly development risks, right? Because now we're not building something completely foreign and new and different. We're in an environment where everything seems familiar, and we can use the own tools, that sort of the tools that we've developed for a long time, and just deploy them somewhere else. So that's your first smart contract right there. Let's just see what it does. First, quick reminder, you know, what does the class actually like do on a normal laptop computer, for example? So here you see our laptop computer. You got the CPU and the memory. And to run a program, you know, number one, you have to somehow have the program on your hard drive. So, you know, today usually this is downloaded by the internet. There's different ways as well. I'm just going to assume you have your program on your local computer. And here's just a little tiny remark on my visual notation. I'm going to stop drawing the CPU here, right? Just because it's a bit distracting. Okay, but you should still think of, you know, this box being an entire computer consisting of, you know, memory and a CPU. Okay, so now we have our program stored in the memory of our computer. Now the user can call the constructor of this program, and so he calls new counter. And what it does is it creates a new instance, you know, in the local memory of that computer, and you know, initializes the instance, you know, sets I to 0 as sort of specified in the constructor. Okay, and then the other thing you can do with a program on a normal computer is you can call a function. So in this case, there was just one function, this inc function. So assume the user calls the inc function, and you know what happens is this, you know, this instance that we just created from the class sort of has their property I increased from 0 to 1. No big surprise here. So how does the same thing work on the Bitcoin computer, right? So again, I assume that we have somehow gotten our the program that we're interested in. We've somehow gotten that into our local hard drive, okay? And now what the user to deploy and create an instance and deploy to the Bitcoin computer, I told you before, what he needs to do is, instead of calling new counter, he's going to call computer.newCounter, okay? Which is this keyword that I mentioned before that allows you to sort of create an instance, deploy to the blockchain. So let's see how that works in detail. When you call computer.newCounter, the first step is that an instance is just created on your local hard drive. Okay, just like in the previous case. But now the difference is that that same object, together with the program that created this object, just gets stored on the blockchain. Okay, it's just a one-to-one copy, right? And that's why we say these two things are now in sync, because both store exactly the same state. Okay, but then if you deploy something to the blockchain, has another nice side effect due to the fact that the blockchain is sort of has this immutable log. We can create an ID for this object, which is just a location on the blockchain where this information was first stored, and this makes it very easy to just assign an ID to every object that's stored on the Bitcoin computer, right? And having these IDs around is also something it's very convenient for programming. It has been studied in the past, for example, in the context of object-oriented databases. But it makes for a computing environment where objects have unique identities and they behave much more similar to objects in the real world, right? So the way the Bitcoin computer will work is you can't just easily make a copy and nobody notices, right? That's exactly the strength of Bitcoin, right? And so in a sense, data stored on a blockchain, it's much closer to our normal perception of just physical objects pretty much. And so that's what's going to make using the Bitcoin computer just an interesting experience, because you really have the feeling that you're shoving objects around and then moving from here to here and stuff like this. Okay, so now we got our object deployed, got ID assigned. So, but I kept going on about this multi-user experience, so let me show how that works. Oh no, before I do that. So we've now sort of deployed this object, but now we also want to somehow update this object, right? And so I told you before, the way in an object-oriented language, the way you change your object is you call a function, okay? And the design goal is to make the Bitcoin computer work as similar as possible to just the normal computing environment that you're used to. Okay, so in the previous step, when you call computer.new, what's returned from the call is an instance of the object, but it's what we call a smart object that knows that it's synchronized to the blockchain and it kind of knows what to do. However, all that complexity is completely hidden from the programmer, and from the outside, that object looks exactly the same way like the counter object would have looked. Right? So it has the exact same functions. The same functions have the same input and output behavior. So now to use my smart object, I can just call the same functions that I would have called on the object that I just created for my local machine. Okay? And when that happens, in step 1, the counter on the local machine sort of gets increased from value 0 to value 1. But since this is also synced on the blockchain, this update is propagated to the blockchain. And now the blockchain also reflects the fact that the counter is now at number 1. But here we're seeing another cool property of the blockchain. This is the effect that the blockchain logs every previous state, right? So we have one piece of data here on the blockchain that represents the current state where the counter is at 1. But we also have another location on the blockchain that throws the counter being at 0. Okay, and so this history of all previous states is insanely useful for many applications, like starting from container shipping, where you want to know where your containers have been previously, to patient records, where you want to know which doctors treated these patients easily. And all that comes very naturally out of the box with the Bitcoin computer, right? And they really just come out of Bitcoin, really. Okay, so now what we want to talk about multi-user things. So assume there's a second user over here. And he also has his own, local computer. To participate on an object that's deployed on the blockchain, use that object, I might say. All that this user needs is this ID of the location where the object was first deployed, right? Or just the object ID. Okay, this guy doesn't even need the actual program. Right? All that he needs to deal with that object is this ID, and really he doesn't need the program because he can look up the program because it's stored right there in the blockchain. So say this user created the object, maybe he'll send the ID to this guy by email. The ID can be made available on a website. So there's many different ways to distributing these IDs, but as soon as this guy now has the ID, if he wants to sort of get his own local copy of that object, what he calls is that second keyword that I mentioned before, computer.sync. And he passes in that ID. And then, the Bitcoin computer understands, he's gonna find that location on the blockchain that corresponds to this ID, and just gonna download, whatever stored right here. So he's gonna download, the source code of the program and the state of the program when it was first deployed, right? Which is an instance of the counter object with I equal to 0. But the system will also detect that this is not the latest state of the system, right? Because these two sort of, versions of the object pretty much are, tightly connected on the blockchain through spending relations. So it's very easy for the system to determine not only that this is out of date now, but also sort of what's the more recent state. Okay, and so the system sort of walks through sort of the entire history of that object until it finds sort of the most recent version. And while it walks down this history, it keeps continuously updating the local copy here until eventually it is in sync. Okay, and now it's probably hard to read, but now all three of these instances are all in the same state where I is set to 1. Okay, and now so we've seen before an example where this guy calls a function on this object, but now this guy has exactly the same copy, so he too can call a function on the same object. So he can call the inc function. What happens is it increases the instance on this local computer to 2. Okay, then it increases the blockchain. Current state on the blockchain is set to 2, and both previous states are recorded. And in the third step, since this guy is also synced, the counter on his local machine also update to 2, right? And sort of that's what creates this illusion where one user calls a function and another computer on the other opposite end of the world potentially updates almost in real time. Okay, the synchronization is going to take under a few seconds. Okay, so it really very strongly sort of creates this impression that everybody's using the one shared device. Okay, so that's what we got here. But then so this is a system that works well, but like to make it more practical, we have to take into consideration that like blockchains aren't free to use. Okay, so every time you store a piece of data on the blockchain, you have to pay, and the price that you pay depends on the size of the data. So we really want to practically store as little information as we must. However, we have to store sufficient amounts of information to ensure that like our second rule is still true, and that like from the information that's stored on the blockchain, both users must be able to sort of gain consensus of the state. Right? But here I think we're being a bit too verbose. So the first thing that you notice is that we're now storing the source code 3 times, right, in each of these 3 locations. And that's just really completely redundant because from this location you can easily find this location. So we don't have to store the program in these in these two cases down there. Then the second problem is when this second guy joined, recall that he had to sort of redo the entire computation of the system from the point where the object was first deployed to the current state. Okay, and so what we're doing here is we're storing all these intermediate states. And so what the system would need to do is you got to look at the state before and the state afterwards, and you have to verify, like in colored points, that this is a legal update. And so in particular, you have to verify that this is an update that's somehow been induced by this class here. Okay, that sounds a bit hard already. So the problem is this class might have many functions in general, and number one, you have to find the function that sort of might take this state to this state. But if the functions take parameters as well, the problem gets way harder, right? Because technically you have to guess these parameters as well. And I don't even know if that's possible. And if it is possible, it takes like a lot of work and it's very complicated. I don't want to do any of these things. But luckily, you can escape that problem fairly easily. So what you have to do is, in addition to the state, you just store the function that was called in addition to the parameters that were passed into this function, right? And then if you have it like this, and you know that the state before was, the counter was at 0, and the state after is the counter is at 1, and I know that, exactly which function was called, the increment function, and I know exactly which parameters, well, in this case, none, okay? Then, to verify that this was a legal update, all that I really have to do is, evaluate the inc function in the context of the previous state, and it should spit out the state after. And if it didn't, someone's trying to cheat me, and I should like not accept that computation, or right, not interact with that person. But now, sort of, that sounds fine, and that works too. But now again, it almost looks a little bit redundant, right? Because why do we even need to store the state, right? If we're going to go ahead and evaluate all these functions anyway, right? We don't need to store the state. We can just have the state be defined by the state here is whatever state you get when you evaluate, this sequence of functions. Okay, and so we can make the system actually quite a bit more efficient by just storing these function calls here. Okay, and so if you think of it, this is a very, very, very efficient encoding actually, right? Because again, if you compare this with Ethereum, what happened here? Okay, a user called a function. Some computation happened. The entire computation happened on his local computer. That is, like I told you, 1,000,000 times more efficient than any computation in a blockchain would be. And all that got recorded here is just the name of the function that's called and the parameters to that function. Okay, and so in particular, the price you pay for that update is just sort of the size of the function name and the parameters. So it's just the size of the inputs. And the interesting thing is what it's independent of. Okay, number one, it's independent of the size of the state, right? Because the state is nowhere stored. We're just storing function calls, and that potentially big state is just created on the local machines. Yeah, which makes it the cost of running a function is independent from the amount of state you need to store your objects, which is amazing. Which is amazing amounts of money, potential for money being saved. And the second thing that it's independent of is the computational cost, right? So just like how many computation steps does it cost, right? So I told you before in Ethereum what happens if you call a function, 10,000 miners in parallel evaluate every single step of that function, right? And here you don't have to do that. You only pay for the size of the name, and the reason you can do that is because you just perform the function on your computer. Right? And that almost sounds too good to be true. It's a smart contract solution where you have a fixed cost that's very low in many examples, and you can evaluate an arbitrarily complex function with it. So why can we get away with something like that? Okay, and the reason that we can get away is our end goal is all users have consensus over the current value. Right? At the end of the day, that's what the users in Ethereum care about, and that's what they should care about, and they don't care what the miners think the value is that the two participants must know, right? And to guarantee that, we just have to make sure that enough information is stored on the blockchain to be able to recompute that state, okay? And sort of by using Bitcoin as pretty much as a dumb storage device, you store all the information that's necessary to sort of recompute that state, right? And it's really not necessary to have someone else recompute that for you if you can just do it yourself. So this is a system that's in some applications going to be much more cheap to use than current smart contract solutions. Okay, and so this is just a picture that shows you we don't actually have to store that information that captures the current state here if we sort of can completely recompute it. Okay, so you get consensus by either having one location where you guarantee that that's the state of the world and just read the state of the world. But you can also get consensus by just sort of getting consensus on how we arrived at that state and being able to replay that on your local machine. Okay, it's exactly the same guarantees, just cheaper. Okay, so what can we build this way? So I just showed you how you build a counter. You sort of have this shared state, which is just an integer, and both users can update that state if they want. And that's actually sort of abstractly speaking is an example for many different things. So think of a chat, right? How would you build a chat? Programming is very similar to there. Just instead of storing a number, you're going to store an array of strings. Every string represents one post to the chat, and you just write a very simple JavaScript program that stores an array, and it has one function called post, and you can post a new string there and adds it to the array. Everybody who sort of finds the root ID of that chat can compute every single message that has ever been called there. Okay, or more examples will be any sorts of public lists. Lists have been popular in crypto for a brief period of time, but also other things like, message boards and image boards, and sort of in general anything where anybody can change the state, right? All these applications can be built like that. Okay, but there's other examples of applications that we really like to build that we can't build with the techniques that I showed you right now. And so in particular, tokens can't be built like that because, like I said, anybody can update the state. And if anybody can update the state, I'll just, reassign all tokens to myself. And that's not going to work well. And then games, you also need restrictions. For example, you need to restrict that, like, if it's not your turn, you can't move, right? And from all these techniques that I showed you so far, there's no way to restrict something like that. Okay, so the problem is that everybody can update the Bitcoin computer whenever they want. Solutions, lucky, very easy, and in fact, it's something that actually the Bitcoin computer excels at, right? Because restricting access is something that's hyper important if you want to do payments, right? You got to make sure that only the owner of the money can send the money somewhere else. And so we'll just use the same exact techniques to restrict access to objects, right? To ensure that only the player whose turn it is can change the state of the board, for example. So let's see how that works. So here's an example of a blog, okay? It contains an array of strings, which will sort of store every single blog entry. And now here we're seeing, one of these two keywords that I mentioned previously, right? We're taking JavaScript, we're adding, two new properties. One is _owner, one is _amount. This is an example that shows you how _owner use, okay? So _owner must be set to a public key, otherwise it doesn't work. And the convention is that only the user who has the private key for that public key is allowed to update that object, okay? That's guaranteed by the system itself and doesn't have to be specified by the programmer. So if you want to set an owner of an object, all you need to do is you just have to assign a public key to that property, right? And so here we see an example in the constructor of the blog object. You pass in a pub key called owner. You set the owner to that owner. And that just means I've just created an object, and nobody other than the person who owns the private key for that public key can update that object. And the second property that we set in constructor is we were setting all the blog entries to the empty list. Nobody has blogged so far. And we have one function that says post a new blog. Okay, and all that it does is this is exactly the code that every JavaScript developer would naturally write if they were to implement a blog on their normal computer, right? So to post to a blog, you pass in your new blog entry, and you just push that blog entry to your array of previous blog entries, right? So that's a very easy way to post to a blog. And then we have a second function here. Okay, so in this function, it's actually interesting to note. So I told the whole story. The important thing about this example is that only the owner of the blog can post information there, right? I don't want other people to post to my blog. I want to be the only person who wants to post there. But in this code, we don't have to write anything like, if, caller is the owner, then execute this call. The system guarantees that already, right? The system will always sort of know who's calling this function, because calling a function involves signing a message. And if the person who calls the function is not the person sort of specified as the owner, it will just do nothing. It will just ignore the function call, right? So even syntactically, very easily can you enforce these ownership restrictions, right? And then we have a second function here called change owner. The purpose of that is, unsurprisingly, to change the owner. And it shows you if I want to give my blog to someone else eventually, maybe I get tired of it, I want to give it to someone else. I can just very simply call a function here, pass in a new owner, right, represented by their public key, and just reassign this owner property. And sort of like here, only the owner, current owner, can change the object and call this function. Okay, but then if he wants to, it's very easy, right? The owner just passes in, here's the new owner, change the variable. At that point, the old owner cannot update the blog anymore. Only the new one can. So let's just walk through this as an example real quick. So in the first step here, we've got user A and user B. User A calls computer.new, passes in the class that we're interested in, blog, but he also passes in the parameters to the constructor. Okay, so the parameter of the constructor is sort of the owner of that object, so he passes in his own public key there. Okay, and what happens is what I explained to you before. The source code of the program gets deployed to the blockchain, and a representation of this this constructor call is stored on the blockchain so that everybody can easily compute the state from there. And now, the owner can call the post function and, post a new message to their blog, right? And again, everybody can read this data. Everybody can determine, what's the latest blog post in this blog. Okay, and so say now, user B, he's the bad guy here. He tries to post something onto user A's blog, despite the fact that he's not supposed to. Okay, and he's not supposed to because in the constructor call, the owner was set to user A, and we add this little circle here to make it clear that these classes or these objects are owned by user A. Now what happens if user B just tries to call a function on that object? The system just rejects it. Okay, nothing happens. So there's and again, this is the security provided by the miners and by the blockchain. Nobody can change the state of an object other than the owner. Okay, but then if if user A wants user B to be he wants to allow him to post something, he just calls the change owner function, passes in user B's public key. This resets the owner of this object, and now sort of user B can post to the same blog. Okay, and so here's another example that just use the same technique. So these techniques that I've showed you so far, there's many examples. So let's just look at a game real quick. Okay, so this is the Tic Tac Toe game. And I started by just downloading JavaScript implementation of of Tic Tac Toe from GitHub pretty much. Any open source implementation is going to work, right? Because the smart contract that I have to write here is extremely similar to just the normal code that you would write if you write code for your local machine. So what are the differences here? The Tic Tac Toe game, of course, must store the current state of the board, but in addition to that, it also stores the two players. Okay, and so we have one property called, that keyword owner property, that's a pub key, and we also, have one other property that can also sort of store a pub key. And now let's look at the constructor of this example real quick. So into the constructor, of course, the constructor will create sort of an empty board, but you also pass in two public keys representing the two players called player 1, player 2. What we do is we set the owner to player 1, which just means is, player 1 is now the owner. He's the only one who can update that object, which is just a different way of saying it's his turn, right? So if it's your turn in a game, you have the power to change the state of the game. And so if you want, like player 1 to have this first turn, we have to set the owner to player 1. And we just store, player 2's public key in the other property. And other than that, it's a completely normal constructor. It does nothing else, actually. The program continues over here. We have two more functions, move and is1. Is1 sort of checks the winning condition, did one of the players win the game? It's going to return either that player or null if the game is sort of still in progress. That function is completely unchanged. That's exactly what I downloaded from GitHub. There's nothing to change here. The move function is mostly the same, one little difference. So the way you update your board, works, in the smart contract exactly like it would on a normal computer. However, since we're dealing with owners, we have to, take care of that. And in particular, we have to make sure that, if I made a move, then I have to make sure that it's now the other guy's turns and they can move. So we got to reassign the owners here. So the way it works is a little tiny bit of logic here is first you check, is the game won? And if the game is won, then you set the owner to be the winner of the game, because maybe, the winner wants to use that to claim some reward, who knows? Okay, like otherwise, if nobody has won, you just swap the two players pretty much, right? You just say, okay, you're not the owner anymore. You're now the other player, and the other player now becomes the owner, which is just a different way of saying, it's the other guy's turn right now. Okay, and so this is an extremely simple implementation, or a simple way to turn an existing game into a smart contract that can run trustlessly on a blockchain on this global computer that everybody even can use, even if they don't trust each other. And so if you can do Tic Tac Toe, you can do every single game like that. Okay, so every single two or multiplayer game that's at least like turn-based game where there's just one guy's turn every time, can be built using exactly that technique. And as I showed you, it's very, very simple, right? You just take your normal game implementation, you add these two players here, got to pass the players into the constructor, and at the end of the move, you have to make sure that like the player whose turn it is the new owner, okay? A very, very large sort of class of examples that can be built like this. So now we can build all these great, like every single game you can think of, and especially games will take advantage of the fact that computation is now free, so you can do games with great graphics and great huge landscapes to explore, and you can all build them as part of a smart contract without having to pay a lot of money. So games is going to be one great application. So you can build tokens like that, and many different applications. However, there's still stuff that we can't build, and like an example would be an exchange or something, right? So maybe some sort of decentralized token exchange or anything like that. And really, what's missing there. At this point, you can probably guess it. It's, we need money, okay? And you can also probably guess that, solution's not that hard because the Bitcoin computer has money built in from the start. So we'll just use, Bitcoin as money. And so let's think of how we can turn this blog example. So in the blog example, we have this change owner function here, which allows, the current owner of the blog to reassign reassign ownership to someone else. So this is pretty much just like giving away your blog for free. So how would we do it if we wanted to sell the blog? Okay, so to sell the blog, first of all, we need some sort of way to store money in the system, right? And so this is where we have this class, money here. It has two properties: an amount, which stores a number of satoshis, and an owner, which is just the public key, and you have the trivial constructor here that just sets the owner and the amount. And you can even forget the send function. Please don't look at the send function. Okay, that's a bug. And now we have, one class, and you can create instances of that class. And, that instance will represent an amount of money. Okay? And like I said before, you have to have enough Bitcoin. If you're going to create an object that stores 100 Bitcoins, you have to have 100 Bitcoins, right? Otherwise, the system will say, sorry, you can't, insufficient funds or whatever, right? But if you have enough Bitcoin, then you can just create any amount of Bitcoin, just store it in an object, wrapped into a normal JavaScript object, store it on the Bitcoin computer, right? And then if you want to buy stuff, in the Bitcoin computer world, that's how you get your money in there, right? You create an object and you just store the amount of money there that you want. And now, if I wanted to now buy this blog here, we have to change, the change owner function a little bit. So I change it to a function called sell. Of course, that has to be done before the smart contract is deployed. Once it's deployed, you can't change the code, but you could, now create this, sellable blog, for example. And it's a very simple function. And if you read it, any JavaScript developer will immediately understand what it means. Okay, so it's a function. You pass in a money object. Okay, and now you got some bit fancy JavaScript syntax going on here. But really, what it does is it says, make who was previously the owner of the money, make him the owner of the blog, right? And make the guy who used to own the blog now own the money. So it's just like one guy got the blog, the other guy got the money, and you just pass in this object here as a parameter, okay? And so again, that sounds almost too good to be true. So how can that work, and how can that be secure? And that just has to do with how the Bitcoin computer is implemented, and essentially with our two golden rules. Okay, so golden rule number 1 said, if you own an object, your agreement is needed when that object is updated. Okay, so let's look at which objects change here. We're setting the owner of the blog to the owner of the money. So clearly the blog instance changes. And to execute that function will require agreement of the owner of the blog. And in practice how it works is he signs a message in a Bitcoin transaction where he says, okay, I see, this function was called, and this is the object that got passed in, and I agree to this update, so I'm going to sign the message. Okay, and then the second object, the second object that's changed is we're passing in this object here by reference. Okay, and so we're passing in the object by reference, and we're changing that object that was passed in. Okay, and again, think of like a physical object being moved from one location into that function. Okay, and now that function changes that object, and by the first golden rule, the owner of that object must agree to that function. Okay, so the way that this will, get implemented is this call is recorded in one transaction with 2 inputs and 1 outputs, and one assigned by the owner of the blog, one assigned by the owner of the money. It's only, you can only sort of use that update if both people sign it, and if they sign it, it's sort of, their mutual agreement to the smart contract. I want to sell you my blog for this amount of money, and the guy with the blog knows how much money it is. The one with the money knows which blog it is, and it's recorded in one transaction, one atomic operation where there's no risk, where one guy sends the money first and the other one doesn't send the blog. Okay, so that's just another example of some very powerful thing that can be done out of the few features that we've introduced today. Okay, so that brings me to the end of my talk. So what I've presented is a novel approach to smart contracts, and it's not like this is way better than everything that has been done before, but I think it's interesting and I think it's different. And my prediction would be that there's going to be applications that are where Ethereum is the go-to tool, right? And people should build these applications in Ethereum. But the two approaches are quite different, so that there will also be other applications where Bitcoin Computer is the more efficient tool to use. And so I'm thinking these are sort of two pretty complementary products, and it's just good to have this new tool in our arsenal, right? And like I said, if you're nostalgic about Bitcoin, you can also just be happy that it works on Bitcoin. Okay, so besides Bitcoin, sort of my whole explanation was very abstract. I make very few assumptions about the underlying blockchain. So when I say Bitcoin in particular, I don't mean any specific Bitcoin. I mean pretty much any Bitcoin-like currency, which the ones we're currently supporting are BTC, BCH, Litecoin, and Bitcoin SV, and hoping to add support for Dogecoin soon. That's cool. But then even beyond that, sort of the general technique would work for many different, and pretty much just every single blockchain, to be honest, right? And so there's lots of flexibility in terms of the blockchain you want to target. You also have lots of flexibility for the programming language that you want to use. We're currently sort of building the prototype in JavaScript, but the general technique works in every object-oriented programming language. Again, because I'm not exploiting anything that's very particular to JavaScript, just talking about very core features that are available in every object-oriented language. So the approach works with many existing programming language, and this is one of the properties that I almost like most. It's very easy to learn, right? And the reason it's really easy to learn is because we have this clear dissection. This is the computer that's always been there, and these are the two isolated things that we're adding to them, right? And that approach allows us to use very well understood programming language like JavaScript and just adding two very simple features to them, right? Which makes it very easy to use, very easy to learn, fun experience hopefully, and also highly secure. So thank you very much. That wraps up my talk. Please go and check out www.bitcoincomputer.io. Feel free to reach out. We're on Telegram. I'm available on email. Thank you very much.